Hello, good morning, dear students. We are now here to discuss with you about the numericals of filter structures. Myself here, Lalit Kumar P. Bhaiya, Associate Professor, Electronics and Telecommunication Engineering Department, Bharati College of Engineering and Technology, Durg. And in front of me, your dear students of BE 6th semester Electrical Engineering as well as Electronics Engineering. A very beautiful and important subject, that is digital signal processing. Till now we have gone through the various videos on the units of this subject particularly, and we have also seen some design problems on the FIR and IIR filters. Now we will go through the filter structures, how the filters can be drawn, or how the filter problems, FIR filter problems and IIR filter problems, can be drawn as a structure. There are different types of structure in FIR and IR. Let us move ahead and see this one. We have already seen this digital filters. About the digital filter structure already we have studied. Here the input-output relation involves a finite sum of products, that is y of n is equal to minus summation k is equal to 1 to n dk y of n minus k plus k is equal to 0 to m pk x of n minus k. Here you can write ak, bk, you can also write, and in terms of the impulse response we go for the h of k here. So this is the basic equation of the linear time invariant system, and this particular equation represents the IIR filter. While except these past values, this equation can represent the FIR filter. On the other, this is written here. On the other hand, an FIR system can be implemented using the convolution sum, which is finite sum of products. This is y of n is equal to summation k is equal to 0 to n h of k x of n minus k. So this can be represented as a FIR filter. And the actual implementation of an LTI digital filter can be either in software or hardware form, depending on applications. In either case, the signal variables and the filter coefficients cannot be represented with finite precision. However, a direct implementation of a digital filter based on either the difference equation or the finite convolution sum may not provide satisfactory performance due to the finite precision arithmetic that already we have seen. It is thus of practical interest to develop alternate realizations and choose the structure that provides satisfactory performance under the precision arithmetic. This is important. Why we need the filter structure, or this structure also called as the realizations. So realizations are important to choose the particular structures to provide the satisfactory performance, optimum performance. Let us go through this symbolic block of to represent the structure or realize the particular filter. This is the adder symbol, which simply x1 of x2 of n. We can add y of n is equal to x1 of n plus x2 of n. Similarly, this can be represented with the help of the sum. These are the structures, these are the symbols used in the structure. Constant multiplier, simply show the arrow and write down here the constant. So you will get y of n is equal to a into x of n, where a is the constant multiplier. This is signal multiplier, x1 of n, x2 of n. This is multiply, you will get x1 of n dot x2 of n. Similarly, delay elements, you can represent Z inverse as a unit delay element, and this is x of n minus 1. You can represent Z to the power minus k for x of n minus k, delayed by k samples. and time advance element can be represented by z. Y of n is equal to x of n plus 1, that is advance by one sample. Similarly, z to the power k, that is x of n plus k by k samples. So these representations are used in the structures. Now, what is the canonic and non-canonic structure? This may be asked for the 2 marks also. Now, let us see, if the number of delays in the basic realization block diagram is equal to the order of the difference equation or the order of the transfer function of the digital filter, then the realization structure is known as canonic structure. If the number of delays, x of n minus 1, x of n minus 2, these are the delays, and if the number of delays is equal to the order of the differential equation, then it is called as a canonic structure. Otherwise, it is a non-canonic realization. So this is also important while realizing the digital filters. Now, this basic structure already I have told you this equation. This is AK and BK. So this AK and BK are the coefficients. AK are the coefficients with the outputs, and BK are the coefficients with the inputs. And this is the transfer function for the basic filter. H of z is equal to y of z upon x of z, summation k is equal to 0 to m bk z to the power minus k upon 1 plus summation k is equal to 1 to n ak z to the power minus k. This numerator provides the poles of the system and zeros of the system, and this denominator provides the poles of the system. So this whole filter represents the IIR filter, while if this denominator term is left, only this term is considered. This is represented as FIR filter. So this is the difference between the FIR and IIR filter. Let us go to the numerical. First numerical on this structure particularly. Determine a direct form 1 realization of the following difference equation. Y of n is equal to b naught x of n plus b1 x of n minus 1 plus b2 x of n minus 2 plus b3 x of n minus 3 and minus a1 y of n minus 1 minus a2 y of n minus 2 minus a3 y of n minus 3. This is the given differential equation. We have to realize in direct form 1. Now you can write this h of z is y of z upon x of z, and you can take the common from here, y of z and x of z, and make this ratio y of z upon x of z. This is the transfer function h of z. So this comes to be a b0 plus b1 z inverse plus b2 z to the power minus 2 plus b3 z to the power minus 3 upon 1 plus a1 z inverse plus a2 z to the power minus 2 plus a3 z to the power minus 3. Now we have to represent this transfer function or this filter in terms of direct form 1 realization. What we do, the numerator term, you can represent this input here x of n or x of z, and numerator term coefficients, this is b0 because it don't have the delay elements. Then you can put one delay element z inverse. So here you will get and put the coefficient b1 here. So b1 into z inverse. So you will get here b1 into z inverse. In series with this z inverse, one more delay element. So you will get here b2 into z to the power minus 2. Here b3 into these 3 elements are there, delay element. So b3 into z to the power minus 3. Add sum all these elements here. So you will get the numerator term. So numerator term always should be shown to the left side here. This is called as direct form 1 realization, in which we can represent here 0 pole form. The left side zeros and right side poles. Here you can show this is the output y of n, and these are the coefficients of the output y of n. Here you can see a1 z inverse. This is 1. This line above upper line represents 1 here. This is 1 plus this z inverse into a1. But along with this A1, you have to put the minus sign, because if we multiply cross here, we will get the minus sign here. So minus A1, that is, this is minus A1 Z inverse, this Z inverse into this Z inverse, minus A2 Z to the power minus 2, this is minus A3 Z to the power minus 3. This will be added here over here, so that you will get the plus sign while taking this cross multiplication, 1 plus A1. So this denominator side is right side, and this right side is called as the pole side. This is the numerator. This is called as a zero side. This form of zero pole form is called as a direct form 1. This is direct form 1. And in direct form 2, what we will do? We will change this side. We will represent pole here and we will represent zeros here. We will see in another problem how to represent in direct form 2 also. And then we will go in by both method, direct form method, that is, we will represent in terms of combine pole zero form. So this is called as a direct form method. So this is a simple numerical which you can go through. Dear students, if you understand this, it's a well and good. Otherwise, you can go through details in the books and my notes also. We will go in the next numericals in the next video, because here we have a particular video limit. That's why we cannot go ahead. In next video, we will go for the numericals. If you have any doubts, you can ask me on mail, phone, WhatsApp or Google Classroom. These are the various platforms on which you can deal with me and ask your doubts and queries. Thank you very much. Meet you in next video. Thank you. Thank you very much.